Welcome to Physics 142. What I'd like to do right now is really briefly review how we calculate the force on a charged particle in the presence of an electric field, and then what we can do with the knowledge of that force. So very briefly, going back to the definition of the electric field, we can easily write down the force on a charge Q that has mass m when it's being acted upon by an electric field E. And you might remember that we define the electric field in terms of the force that a positive charge feels. And so the definition for that was E is equal to the force divided by the charge. So if we just turn that equation around, we can solve for the force and say that a charge Q, which can be either positive or negative, multiplied by the electric field strength, gives us the force. And so again, if the charge is positive, then the force will be in the same direction as the electric field. If the charge is negative, it will be in the opposite direction. So, if that's the only force that's acting on the charge, then we can also employ Newton's second law to take the force in terms of the electric field and relate it to the acceleration of the charge. So that assuming it has a mass m, this force QE is equal to the mass m times the acceleration a, and solving for a, we get QE divided by m. And you might remember that in kinematics, the acceleration was the important quantity. If we know the acceleration, then in principle we can calculate the velocity, and then knowing the velocity, we can then calculate the position as a function of time for the particle. So using all the knowledge of kinematics that we built up in the first semester of the course, we can now analyze the motion of the charge. Notice too that if the electric field is constant, if it does not change in time, and if it's uniform, so that it stays the same value in the same direction everywhere in space, then the acceleration will be a constant, and we'll have constant acceleration motion. So we already know how to handle that from our simple discussions of kinematics in the first semester. So now, let's look at an example problem. Here we have an electron that has mass m and charge minus e, where E is the fundamental charge, 1.6 times 10 to the minus 19 coulombs. This electron's initially traveling in the positive x direction with a speed v0. And when it gets to the origin, in this graph, it enters a region of a uniform electric field pointing along the positive y direction. And that electric field is uniform in a region of width, capital D. So ignoring gravity, we want to use our knowledge of kinematics to find the deflection of the electron due to the electric field. And the deflection is the downward deflection that the electron will experience from the time it enters the electric field at the origin until it gets to the end of the electric field region at a coordinate x equals capital D. And so it will be right here on the sketch. And then also we would like to find at that point what angle the electron's velocity vector makes with the x-axis. So when it gets to this point at a coordinate x equals capital D, it will now be at a coordinate y equals negative d, and what will be, if the final velocity vector is along the trajectory direction at that point, what will be the angle that that velocity vector makes with the horizontal axis? So I'm going to switch over to my sketch pad and solve this problem. Before actually getting into the solution of this problem, it's important to look at the sketch to see why the electron's path is shown the way it is. Remember that an electron is a negative charge, and therefore we know from what we just talked about a minute ago that when we've got a field E, that the force is equal to the charge times the electric field vector. So since the electron, it has a Q that's negative, right? Q equals negative E here, then the force will be opposite to the electric field. So in this region of space, the electric field is in the positive y direction. Therefore, the force, as the sketch indicates, is in the negative y direction. So it's a constant force, and the electron will follow a parabolic trajectory, deflected downward. And so we're going to look at the electron's displacement from its original position, entering the electric field at the origin, to the final point over here. We would like to find the y coordinate of this final point. That's what D is asking for. How far downward is it deflected? So remember from constant acceleration motion that we have some very simple kinematic equations that we can use. Delta x is equal to v0 xt plus 1/2 ax t squared, and similarly delta y is v0 y t plus 1/2 ay t squared. And the x and the y direction displacements are independent of one another. They only depend on the initial components of the velocity and then the x and y components of the acceleration. And this is going to simplify quite a lot. If we look at the first equation, we know that the acceleration in the x direction is 0. There's no force in the x direction, and therefore that second term drops out. Delta x, what's the change in x as it moves from the origin to the final point? Well, we realize that that is capital D. So this equation here gives us that capital D is equal to v0x times t. v0x, well, its original velocity in the x direction is v0, so when it first gets to the origin, that's exactly the x component. The x component is simply v0 because it hasn't started to deflect downward yet. And so this, if I solve this equation for t, I'll be able to use it in combination with the expression for the displacement in the y direction. The displacement in the y direction is really what I'm trying to solve for. That I'm going to call d. And so d, actually I should call it negative d, right? Because if d is just a distance, we know that the final y coordinate is negative. The initial y coordinate is 0. The final y coordinate is negative d. So delta y is negative d. v0y, well, initially when it enters the region of the electric field, it has no y component of its velocity. So that term is 0, and we're left with simply negative d is 1/2 ay t squared. Now what's ay? Let's go back to the expression for the force. Remember then that q times E is equal to m times a according to Newton's second law. So a is QE over m. Q is negative little e, so it's minus e over m. Therefore, and since that acceleration is in the y direction, the y component of acceleration is minus little e big E over m. So that's what we will plug in to this expression for a sub y. Then we'll also plug in the t that we got from the expression for the displacement in the x direction. So we're going to take the expression for a sub y, plug it in on the right-hand side, and take the expression for t and plug it in on the right-hand side. So this becomes 1/2 times negative EE over m times big D over V naught squared. And note that the minus signs on both sides of the equation cancel out, which makes sense because D is just a distance. But when I put the minus sign in, I guaranteed that this would work out properly. So D is, we're just going to get little e, big E, capital D squared, all over 2m v0 squared. And that is as far as we can go with the given information, because everything else that's in this equation is either a constant of nature, like the electron's charge and its mass, or one of the pieces of given information, like the electric field E, the initial speed v0, and the horizontal distance over which the electric field acts, which is capital D. So that's our final answer for part A. For part B, what's the angle the electron's velocity makes with the x-axis? Well, again, we're looking at, I'll exaggerate the length of it here, but we're looking at the electron's vector v right when it exits the electric field. And the sketch is correct. It will continue along a straight line trajectory because when it leaves that region, there's no more force to act on it. No force means no acceleration. No acceleration means that the velocity doesn't change. So this v pointing down and to the right, I will actually sketch it over here. That's v, and exaggerate a little bit. and realize that there's a Vx and that there's a Vy, and that the angle theta is related to those two components through the tangent, right? Tan theta is equal to Vy over Vx. So if I can find Vx and I can find Vy and take the ratio, that will give me the angle. So how do I do that? Well, remember, for constant acceleration motion, not only do we have equations for the displacements, but we also have equations for the x and y components of velocity. So Vx is equal to V0x plus axt. We know that the x component of acceleration is 0, so Vx is simply V0x, and remember, that's just V0. The particle is traveling to the right. Its initial velocity is only in the x direction, so V0x is V0. Vy, same kind of equation, equals V0y plus ayt. Well, V0y is 0 because initially it has no component of velocity along the y direction. A sub y, we already have an expression for. T, we have an expression for up here. So if we just make those substitutions, ay is negative e over m. T is d over v0, like that. So that's my Vy, and the tan theta then is simply Vy negative, let's see, the denominator is just going to be V0 because that's Vx. The numerator is minus little e big E d over m V0, so this gives me minus little e big E d over m V0 squared. The minus sign tells me that the angle that I get, if I were to plug numbers into this equation, if numbers were provided, the angle that I get would be negative. And that makes sense according to the sketch because normally we measure angles in the positive direction in the counterclockwise sense from the x-axis. This one would be in the negative direction, the clockwise direction. So the angle would be negative. But there's really not much more I can do from this point. I suppose I could take the inverse tangent and write down that theta is the inverse tangent of this expression in the box, but that's about all I could do. So we'll consider that we're done here. We've shown that we can relate the initial velocity and the strength of the electric field over this distance capital D to the motion of the particle. And we can find the deflection that it suffers as well as the final direction of its velocity vector through the angle theta. And this should be relevant to some of the homework problems that you'll have to do on this assignment. I'll see you in class.